Alright, let's continue our discussion in this welded connection topic. We'll first discuss the preliminaries before we get into the details of the code provisions. Now, let me present to you a configuration of the weld length with respect to the loadings or load direction. Okay, so let's say this is our load P, and then this is our load P. Now, for this case, what if I'll weld it here? So meaning that the weld length is perpendicular to the loading direction, and we say this is L, meaning that's the weld length. And for the second case, let's say it's not actually 90 degrees here. What if I'll cut a portion, and I'll provide a weld length, of course, of a length of L, meaning it has the same length, except that the angle is this angle is of course that's 90 degrees. This one is 90 degrees, so meaning here theta is 90 degrees. This one theta is less than 90 degrees, but greater than 0. And here, what if the weld length is along this direction? Of course, that's gonna be L over 2, and then this one is L over 2. So meaning that uh, we are considering the same weld length, but at different angle from the load direction. Let's say this is 0 degrees. Now, if we plot this, what we actually see is that and this is the load, weld load, and here the deformation, normalized weld deformation. Now, for theta is equal to 90 degrees, this is it. Theta is equal to 90 degrees, and then this one theta is this one greater than 0 but less than 90 degrees, and this one theta is equal to 0 degrees. Okay, so we see that um, the weld length that's perpendicular to the loading direction, it produces actually the highest weld load capacity, and as the angle decreases, then you're actually decreasing the strength. Okay, so you'll see it here. You have a decreased strength compared to the 90 degrees. Now, this 90 degrees is referred to as the transverse weld, and then this one is the longitudinal weld. But another thing to observe here is that for this 90-degree weld, we have this deformation, and this one for the 0 degrees, we also have this deformation, meaning again that we have a deformation or a plastic deformation for a 0-degree weld, whereas here this is a brittle weld joint. Although it is strong, it is brittle. And again, when you say brittle, it means that it can fracture immediately, or it fractures without going under the plastic deformation. Alright, now let's move on to the concept of effective throat and effective area. And effective area. Okay, so let me draw this first. This lap joint, and let's say this is my fillet weld over here. Okay, so this is my weld. Of course, this is an idealized shape for the fillet weld joint, because the actual ones, it has let's say this is our idealized line, but the actual one, it could have some materials over here, weld materials, and it can also have materials over here for the penetration, but we will only consider a um, triangular shape. Okay, so the size of, when we say size, the size of a fillet weld is this one. That refers to this base, and then this opposite side of the right triangle. So this is the size. And if we weld it along a length, so something like this, so let's say this is the weld length, then our symbol that we'll use is L sub W. Okay, that's the length of weld. And this section that is considered to be effective in carrying the load is this throat. Okay, so the throat is the distance from this root, okay, from this root perpendicular to this hypotenuse. Okay, so that is the throat. So in this side view, this throat is the distance from this root up to here. Okay, so this is the throat, and the area, if we multiply the throat to this length, then we get an area. Okay, so this is the shaded area, and this is the effective area for carrying the loads. Okay, so what's the value of this? If we have this A, this weld size, and let's say for the throat we have D sub E, for example, this is just equal to 0.707 times A. Okay, so that's the throat length, or just the throat. And the area that we'll use in our computation is this shaded area. That's called effective area, which is just equal to the throat times the length. Okay, so now let's move on to the code provisions, because we already understand this basic nomenclatures in this fillet weld configuration. Okay, so for the code provisions, we have them. You will start in this limit states. So again, limit states, they're actually the basis for the analysis or the design. And we have a limit states of we actually have 3 limit states, which is the weld metal failure. So meaning that let's say we have this welded joint, and we have this fillet weld right here, for example. So it is possible that this joint will fail in this weld metal, the weld metal itself. So that's one limit state. And the second one is, it could be that instead of this weld metal failing, the part that fails will be this base metal. So it could be this base metal or this base metal. Okay, so let's write here base metal failure in either yielding or base metal failure in shear. This one is also shear. This is shear yielding, and the other failure could be shear rupture or fracture. Okay, so that's our limit states for these welded joints. Again, weld metal failure, it means that this weld material can fail, or we can have a base metal failure, meaning that this base metal, will fail in either yielding or shear rupture. And since we have two parts here, then we have to check the two base metal. Okay, so how do we compute for the strength of weld metal? Okay, so strength of weld metal. We have Rn, the strength of weld metal per length of weld. Okay, so per length of weld can be computed by this equation. That's the strength of weld, that's F sub W, and times the area. So strength is just simply this capacity strength in terms of the load. This is the load capacity. This one is the strength, and this one is the area of the weld. Okay, so it's just the basic stress equation of B over A. If you recall that, it's just the same, except that what is this strength and then what is this area of weld. Now for the strength, we can actually obtain that in table in our lecture handles. We have table 14-2. So meaning if we have, for example, A6013, then what's the minimum yield strength in megapascals? So here it says we have 345, and this one is 425. For example, we have E70 7018, and this one Fy is 415, 485. Okay, so it's already tabulated, but we're actually taking the shear capacity. So it's not just the Fy, but rather this is the 0.6 Fy, or F. Of course, we say Fy. Sometimes we say or we refer to the steel, but here let's just denote it as FEXX. Okay, so 0.6, again, that's a relationship for the shear capacity to the yield strength. So this is 0.6 FEXX, and this A, area of weld, this is the 0.707 A, and if we multiply that by this length of weld, that's actually the area. Sorry, if this is the area, then this should not be in terms of length. Okay, so recall that this area is the throat area. Okay, so this is the area. This is our A. This distance is our effective throat, and then this is our weld length. So therefore, we can rewrite the equation for the weld length as Rn is equal to 0.6 FEXX times 0.707 A times the weld length. Now, if in terms of length, we get Rn per unit length is 0.6 FEXX times 0.707 A. Okay, so why do we have to transpose this equation to this one? It's just simply because recall that that there's a different capacity if we're welding along the load direction, and along, or if we have a weld in this direction, perpendicular direction, we have a different capacity. However, for simplicity, actually this one is, there's actually an equation, and that's actually 1.5 times, but here let's say this is just 1.0, so meaning you have a 1.5 times greater strength for this transverse weld. But for simplicity purposes and in many reference texts, the computation is just simply based on this. Okay, so it's something like this. This is going to be an extra strength for this 0.5, this 1.5. So we have to express it in terms of this, because sometimes this is more handy, because once we know this, then we just have to multiply the length. Okay, so what if there's a combination? There's a combination of this longitudinal weld and the transverse weld, because this equation would be only true if you have either a longitudinal weld, or you can have a purely transverse weld. Okay, so this one is for this. But if there exists in a welded joint a longitudinal weld and a transverse weld, then you have to check the maximum. So we have this V Rn is equal to theta times the maximum of the two conditions. We have the weld length, that's longitudinal, the R sub W times L plus R times W times T, W sub, R sub W times T. Okay, so meaning what's the strength in this longitudinal section, and what's the strength in this transverse portion, or 0.85 RWT plus 1.5 R, sorry, this is L, then this one is T. Okay, and this reduction factor is 0.75. Okay, so again, if we have a problem that's just purely longitudinal or purely transverse, then this will be the equation. Then you just have to multiply it by the whatever length there is in the problem. But if we have a problem that has both longitudinal and transverse, then we have to check this condition. Okay, so now let's discuss the strength of the base metal. Now, for the strength of base metal, we have we can also write it in terms of per unit length. So simply it's just the strength times the area of the base metal. That's the typical notations that we have. So this is the load capacity, and this is the strength, capacity. This is the area of the base metal. We can rewrite this as 0.6 FYT, and this one is for yielding. Take note, shear, yielding. And this one, for the shear fracture, shear rupture or fracture, that's also the same. It's the capacity, of course, in terms of fracture, times a area, which is 0.6 FU D. Okay, so take note of the 0.6 Fy. This means that this is our shear strength. So this one 0.6, this is our shear strength in rupture, shear strength for yielding. And T is the thickness. Okay, so thickness of the base metal, of the base metal. Okay, so what else? Of course, that's per the weld length, so we just have to multiply that in that or by that weld length, okay, to get the total. Okay, so therefore the design capacity VRN is equal to the minimum of the three condition. By the way, we'll also multiply a reduction factor here, but the you would notice that even though they're the same, 0.6 Fy and 0.6, I mean 0.6 Fy and 0.6 Fu, so you might think that this one would give a higher value, of course, because the ultimate strength is greater compared to the yield strength. But since there's a reduction factor, there's gonna be a difference in the value. This one, the reduction factor for this is 0.75, but this one is 1.0. So that's why we still have to check whichever will give the, I think that will give the minimum. Okay, so if you write it here, we have 0.6 FEXX times TE. Okay, so that's the throat times the weld length, of course, and this one is 1.0, 0.6, of course, times the weld length, and this one is 0.75 times 0.6 FUD times the weld length. Okay, so whichever would be the minimum, that's gonna govern the strength of the welded joint. Okay, so now let's talk about the minimum size of fillet welds. So there's actually the size of weld depends on the thickness of the thinner part. So example, we have this let's say this thickness of the base part. Then let's say what's gonna be the minimum size, or what's gonna be the maximum. Okay, A mean, or let's say what's gonna be the maximum. Okay, so for the A mean, we can obtain that from the table. That's in our lecture house, as table 14-3, and of course this is just coming from the code. So it says here, if we have a thickness, for example, 6 mm and lower, then our A is equal to 3 mm. But if we have, let's say, 6 to 13 mm, this is the thickness. Whichever is the smallest. It says here we have a 5. A mean is 5 mm. Okay, so you can just obtain that from the table. For the maximum, for the A max, we have two conditions. So um, if our material is less than 6 mm, so we just use T. Okay, for this less than 6 mm. But if it is greater than 6 mm, then T minus 2 mm for T greater than. Okay, so that's our A maximum, meaning that we still have, you would notice this minus 2, then that's actually a minus here, that's the 2 mm. Okay, so that's gonna be the maximum. And what else? We have maximum effective weld length. Effective weld length. So meaning how much length should there be, or the minimum should be equal to for A at least. Okay, so the weld length minimum should be at least 4 times the size. All right, now let's discuss the procedure for analysis. For this analysis, meaning that we are already given this geometry of these welding connections and the specifications and things like that. The first step to do is to find or to obtain the necessary information. So, for example, we have a problem and it says we have an East 7018 welding rod. I mean the welded joint, and then the base material is A36. Then we have to find the example. What's the FEXX? What is the what else? What is the FY or FU of the base metal? And once you have obtained that, then you have to calculate the weld metal capacity and check. Um, the next step is to calculate the base metal capacity. Okay, since we have two, then let's say shear yielding. Then for the number 4, calculate the base metal capacity. That's going to be shear rupture. And once you've done that, then you can find the minimum to determine the design capacity. After that, you have to check the weld limitations. Okay, so weld limitations meaning the A mean, or the weld size, the minimum weld size, the maximum weld size. Okay, so I guess in the next video we will do a problem on this welded joint.